Assalamu alaikum. Welcome back to the Fine-Tuning of the Universe lecture series. We have finished the fine-tuning of the masses of the fundamental particles, and this is a perfect segue to a difficult topic, one that is typically not at all discussed in elementary presentations of fine-tuning, and that is the fine-tuning of the Higgs boson. And this discussion will be the most difficult part of the course, this sub-series of lectures. I find it to be the most fascinating and most spiritual part of the course, and I hope that you will hang on for the ride and enjoy it, inshallah. And so let us begin by asking the question, what in the world does that even mean? So the discussion here will center around the Higgs boson. And as I said, this is usually not discussed because to understand the fine-tuning of the Higgs boson requires a lot of background. Understanding the fine-tuning of the mass versus expansion rate at the Big Bang, that's pretty straightforward. That if we expand too fast, it is impossible for the mass to coalesce into stars and planets. If we expand too slowly, then gravity will take over and we'll get a big crunch before stars have had a chance to develop. The interest there is in looking at the parameters and how precise that fine-tuning is. The masses of the fundamental particles, again, little more involved, but understandable. This notion of the Higgs boson really requires a lot of background, but that background, I think, is very, very important and interesting for people who are people of faith who also have an interest in science, and it is beyond, of course, what we typically covered in high school, even in a college physics course, unless you particularly specialized in physics. So the Higgs boson is, something we really didn't talk about much yet. We've talked about the three generations of matter particles, the so-called fermions that are made up of the quarks and the leptons. And we said that all matter is made up of the up quark, the down quark, and the electron. And we also noted the electron neutrino. And we touched on these particles here that are known as the gauge bosons. And they are sort of the force carriers. The gluons for the strong force, the photon for the electromagnetic force, and the W and Z bosons for the weak nuclear force. And then up here in the corner, we have the Higgs boson. And while we're here, we will once again note the significant difference in masses between the electron, which is 0.5 roughly MeV, million electron volts, and the quarks, which range in mass from 4.5 to 9.4 times as massive as the electron for the up and down quark, to hundreds of thousands of times more massive for the higher generation quarks, and significantly more massive for the cousins of the electron, the second and third generation particles in the electron family, the muon and the tau particle. And so we will just note that they have mass. We will note the little zero up here that the gauge bosons, we have the gluons don't have mass. The photons don't have any mass. They're just the photons of light that you're very familiar with. But the W and the Z bosons do have mass, and that mass is, in the range of 80 to 90 giga electron volts. So significantly higher than an electron. For reference, a proton is about 1 giga electron volt, a little bit less than that. So these are, say, on the order of, roughly speaking, 100 times as massive as a proton. So in particle physics, that's pretty big. These are all force carriers, some of them without mass, some of them with some pretty hefty mass. And then this Higgs boson even more massive, 126 gigaelectron volts, so like 130, 135 times as massive as the proton. Okay, so we're again focused on the Higgs boson here, and we can cut right to the bottom line that the Higgs boson is important. It has a mass that's written here as 126 gigaelectron volts. It's maybe a little closer to 125 gigaelectron volts, but in any case, that's heavy. It is about 135 times the mass of a proton. And when theoretical calculations are done, this Higgs boson is supposed to weigh about a billion gigaelectron volts, 10 to the 18th gigaelectron volts. That would be disastrous for life as we know it. However, through a miracle of fine-tuning and cancellations between the so-called bare mass of the Higgs particle and the quantum corrections to the mass, that billion gigaelectron volts is cut down to 126 or 125. So basically, we slice off 10 to the 16th of those 10 to the 18th gigaelectron volts. And we could just leave it at that. But I'm sure you'd be very unsatisfied with that. Because what is the Higgs boson? Why is it important? What is going on? And what is going on here is one of the most beautiful, intricate stories in science. It is at the heart of the standard model of particle physics. And I know the standard model is not an exciting name, but scientists concur that it is the pinnacle intellectual achievement of humanity. And the Higgs boson is sort of central to that achievement. So we would want to know about it. And so to begin exploring, let us ask a question. Is mass a fundamental property of particles? In the previous slide, we talked about the range of masses of these particles. And I'm sure that when we think of a particle, we automatically assume that, well, it will have some mass. Some particles are heavy, like the top quark and the bottom quark. Other particles are light, like the electron, or extremely light, like the electron neutrino. But if you are a particle, you have mass. But it turns out, actually, that there are two kind of revolutionary ideas. First, mass is not a fundamental property of particles. Again, to cut to the bottom line, mass is a derived property of these particles interacting with the so-called Higgs field, and the manifestation of the Higgs field is the Higgs boson. And the analogy that's usually given is if you imagine walking through a room, that's easy. If you were to fill that room with water or with honey and try to walk through it, that would be a lot more viscous and there would be drag. And it is the drag on the particles as they try to swim through the Higgs field that gives them mass. So fundamental idea number one is that mass is not a fundamental property of particles. And I'm sorry for using the word fundamental twice, but critical idea number one is that it turns out that mass is not a fundamental property of elementary particles. An even more revolutionary idea is that while we said that everything in the universe is made up of these three particles, up quark, down quark, electron, and then we have these other heavier generations that are very similar to the first generation, it turns out that cutting-edge physics is now telling us that we are not made up of particles at all. That everything is actually made up of fields, not particles. And you know what a field is. You've heard of electric fields, magnetic fields. The example usually given is a temperature field. In the room that you're sitting in, you can go to every point in the room and get a temperature at that point. Normally, we just measure the temperature in quote unquote the room. But you know, the temperature may be a little cooler next to the window, a little hotter next to the heating vent, etc. If you were to go to every point in space and give every point in space a value with the temperature at that point in space, now you have mapped out a temperature field in the room. So that's roughly what a field is. And it turns out that an electron, for example, is not really a particle. It is a local excitation of the electron field that permeates space. Same with the up quark, same with the down quark, and so on. So we are not made up of particles. We are made up of fields. And so when we say that the gluon is a particle or the photon is a particle, what we really mean is that these are also fields, and these are manifestations of the gluon field and the photon field and the W and Z boson fields. And these particles here, now I'm again lapsing into calling them particles because that's what everybody does. They are gauge particles or gauge bosons, and these particles here are all fermions. But all particles are local excitation of fields. And that is a pretty interesting concept. But what is even more interesting and more fundamental is, what does all of this imply about the underlying structure of the universe? Before we get there, though, I want to enthuse you to keep going because this is probably starting to sound pretty esoteric. This Higgs boson was a pretty exciting discovery. It was discovered or confirmed in 2012. Here is an article from the New York Times, July 4th, 2012. You see all of these people cheering, but they're not cheering because it is the 4th of July. These are scientists in Geneva at CERN looking at the results of the most recent experiments from the LHC, the Large Hadron Collider, that confirmed the existence of the Higgs boson. And this ended a sort of 50-year search for the Higgs boson. The Higgs boson was first theorized in 1964 by, the name associated with it, of course, is Peter Higgs. It is named after him, but several physicists contributed. One of them is Francois Englert, and in 2013, Englert and Higgs shared the Nobel Prize for the discovery of the Higgs boson that had been theorized almost 50 years earlier. And this discovery is so critical, so central to our understanding of the fundamental structure of the universe, that it kicked off a 50-year search. And you see the article here in the New York Times beginning by telling us that this was the end of one of the longest, most expensive searches in the history of science to finally discover the Higgs boson. So I hope that this interests you to kind of continue to figure out, why is the Higgs boson so fundamental? Why was the most expensive scientific instrument in human history, the Large Hadron Collider, the big particle smasher, built to confirm the theoretical existence of the Higgs boson? To begin answering that question, I would actually like to focus on a verse that we will bring up again and again in this lecture, because as I said, I think that this is the most spiritual part of this lecture series. And this is a verse from Surah Al-Ahqaf, and the verse says, أعوذ بالله من الشيطان الرجيم ما خلقنا السماوات والأرض وما بينهما إلا بالحق وأجل مسمى. Let me just stop at this portion of the verse. We have not created the heavens and the earth and all that is between them otherwise than in accordance with an inner truth and for a term set by us. And I want to focus on this notion that the universe has been created with an inner truth. It has been created with nothing except al-haq. ما خلقنا السماوات والأرض وما بينهما إلا بالحق. What is this inner truth? What does this mean? I'm sure we all have our ideas. Of course, in the philosophical moral realm, I think it implies that the universe has not been created haphazardly. It has been created with a purpose, and that purpose is in the service of truth, the big truth that God exists and that He is the creator of the heavens and the earth, that it is created according to moral principles, in moral truth. But I believe that it also has a very significant set of scientific implications. At the first level of this onion, the most superficial level, this truth can be understood as the unchanging laws of physics, the natural laws that govern the universe. I think as we talk about the Higgs boson, we will get a more nuanced view of what this truth may mean. I don't ever want to say what it means. God knows best what it means. But I know that as I have studied physics, my understanding of what does it mean, what is this inner truth, has evolved. And that evolution is really intimately tied up with the story of the Higgs boson.